hypothesis testing. So remember, now we are dealing with vectors, not just scalars, right? So in general, our x is a vector. So we need more general concepts and tools to conduct hypothesis testing. So the test we are going to talk about is called the wall test. So it is the most general test. It can apply to any estimators that are square roots of n asymptotically normally distributed. So let's see. So suppose we have a estimator theta hat, which is square root of n asymptotically normally distributed, and we have a non-stochastic matrix Q by P matrix R, which rank equals Q. So the matrix represents the restriction we want to test, or the hypothesis that we want to test. So it is not a, it's just non-random, okay? And in this case, it is linear, right? It is a matrix, so it is linear. So these are the linear restriction that we want to test. We know if we multiply a normal distribution by a non-rendered linear matrix, then it remains to be a normal distribution, and the variance will become its quadratic form. Also, we know a quadratic form like this construct from a normal distribution will follow a chi-square distribution. Right? Remember, a chi-square distribution is just the square of standard normal distribution, right? And essentially, this is what we do here, right? So the middle term here is essentially we sort of standardize the normal distribution first, and then we take the square, then it becomes a chi-square distribution. So yeah, so this is pretty straightforward. Note that, okay, so there are still some unknown here, right? So okay, so let's see. So first of all, so we don't have V yet, right? So V is the variance from the normal distribution. We don't have that, but usually we can easily get a consistent estimate for that, right? So suppose we do have that, we call V hat, and we can just put V hat here. Then yeah, we put a V hat here, and we put the square root of n together in the middle, so that will be n here, and the whole thing will converge to a chi-square distribution. So notice that there are still unknown, right? So theta still unknown, right? Theta is still unknown, but that's fine because theta is exactly what we want to test, right? So what is a statistic? We have already seen the term statistic quite often. Statistic is a function of sample that measures some attributes of the sample. Okay. And now we can construct something called wall statistic. Okay. And we have the hypothesis. The null hypothesis is r times theta equals small r, and the alternative is r times theta does not equal r. Okay. So now we can replace the r theta here. We can replace r theta here by the small r, which is known, right? Which is the number we want to test. So we know what is small r we want to test, right? We may test like, okay, that's maybe 0, maybe 1, or other number. But these are the number we know. And so suppose, so under the null hypothesis, so if the null hypothesis is true, we actually know the distribution of the whole thing, right? So here, because there's a known theta, so we cannot calculate this thing. We cannot calculate this whole thing yet. But under the null hypothesis, r theta equals small r, so we can actually calculate the wall statistic. And we also know that the wall statistic follow a chi-square distribution. Okay, and that's how we conduct hypothesis testing, right? Because now everything we can calculate, and we know their distribution. Recall that if you divide a chi-square distribution by its degree of freedom Q, it becomes a F distribution. Also, a one-dimension F distribution is the square of a T distribution. So in fact, t-test is a special case of f-test. T-test is a one-dimension f-test. So here we have asymptotic t statistic and asymptotic f statistic. Right? If your restriction R is only one dimension, then we get an asymptotic t statistic. In general, we have a asymptotic f statistic. So in fact, software like Stata will calculate W, the wall statistic first, then divide it by Q and call it F statistic. Similarly, it will calculate the wall statistic, take the square root, and give you the T statistic. And note that the wall statistic here, or the F statistic, does not need homoscedasticity. So in undergrad textbooks, sometimes we say, oh, if you want to get F statistic, you need to, there's a formula to get F statistics based on R square, but that requires homoscedasticity assumption. In general, actually, we don't need that. Here, we are okay to have heteroscedasticity, right? As long as that is a consistent estimate for the variance, that's fine. And we don't need it to be homoscedasticity. So let's see. Now we know we have the tool, we have the wall test, and we know how to calculate the wall statistic. Let's go back to the OLS case. Okay. So let's say we want to conduct inference for OLS, and we want to apply we want to calculate the wall statistic. Okay. So first of all, we needed to have the variance of beta hat, which we already have, right? Then we can use it to construct a wall test. So let's say this is the null hypothesis R beta equals R, where R is a Q by K matrix, and this is the alternative. And we already showed that beta hat is square root of n asymptotically normally distributed. Right, this is what we have shown previously. Now, if we multiply it by R, it remains to be a normal distribution, and the variance becomes a quadratic form, a bigger quadratic form here. Right? It's a bigger quadratic form. Then again, under the null hypothesis, we can replace R beta by small r, and we can calculate the wall statistic. So R beta hat minus small r, and it's a full quadratic form. So in the middle is the OLS variance, will converge in distribution to a chi-square distribution. Okay, and from this known distribution, we can conduct our statistical inference. Right, we can know whether it's significant at 5% level or 1% level. Okay, right, here is a quick example. Right, like say we have a model like this. This is a linear model, and we want to test the restriction here. How to write down the matrix R? Well, so first of all, X is X vector is 1. The first component is 1. X1, X2. Right, and beta equals beta 0, beta 1, beta 2. Right, and the restriction here is the R. Beta 0, beta 1, beta 2. become beta 1, beta 2. Right, so that shows, yeah, this is exactly the restriction we want to test. So this is just an R matrix. Okay, so now, so here remember, so here the R matrix is linear. Right? We can only test the linear restriction. Right? We can test whether beta 1 plus beta 2 is 0, or beta 2 plus beta 3 is 0. But what if we want to test nonlinear restrictions like 1 over beta or beta 1 over beta 2? The vortex can actually be generalized to nonlinear cases using the continuous mapping theorem. But to do so, first of all, we needed to get the asymptotic variance for the nonlinear combination first. And the method, and it is called the delta method. Right. So note that, so let's come back a bit here. Go back here, let's see something. Okay. So here, so this guy here is actually the variance of this, essentially the variance of R beta hair, right? It's essentially but this is linear, so it's just a linear function of the original variance beta hair, right? It's just a linear function because R is linear. But if we have a nonlinear restriction, then that will become quite tricky because you will need to get the variance of a nonlinear function of beta hair. Okay, and in general, that would be extremely difficult to get. It's actually quite difficult, but there's an easier way. Is called the delta method. Okay, so the delta method is actually a very clever way to get the variance for nonlinear function. So let's see. So what is the delta method? Okay, so again, suppose we have a square root of n asymptotically normally distributed estimator theta hat. Okay, and it is consistent. And there is a function g that mapping from Rp to Rq, and it is continuously differentiable. So that means its first derivative remain to be continuous. Then we can show that the square root of n. So we can show that actually, if theta hat is square root of n asymptotically normal, then g theta hat is also square root of n asymptotically normal. Right? It's still normal. Not only that, we can also get the variance. Its variance has a very simple quadratic form based on the first order derivative. The g here is called the Jacobian, which is the first order derivative of the function g. Okay, and it is actually linear, right? So it's just a matrix, right? So it's sort of simplify the thing. So we use the first order derivative to. It's actually a bit like Taylor expansion, right? The whole function could be quite complicated, but we use the first order expansion or first order approximation to get the variance. And it actually will be true. It's actually not just an approximation when the sample size become larger, when the asymptotics hit. So here is a sketch proof for the scalar case. Okay, how the delta method work. So start here. So this is a function, and we know by the mean value theorem, it can be rewrite like this, right? And the theta star must be between theta and theta hat, right? So, if you remember what is mean value theorem, okay, let's say we have a function like this, and this is a, this is b, this is fa, this is fb. Right, so we know, so this is a, sorry, b minus a, this is fb minus fa, right? So we know that fb minus fa will equals b minus a times f prime c, right? Because we can find the slope here, that's the same as this guy here, right? And this is the point c, right? The slope here, the same as slope here, so b minus a times the slope f prime c will equals fb minus a, will equals this guy, right? Times the slope here. And that's the mean value theorem, and we already talked about that in the math revision. Okay, and if we apply that here, so we know we can find a g prime theta star here. And we do a trick here. Then we rewrite this guy, g prime theta star, and so we rewrite the whole thing. So basically we add g prime theta times this guy, and we minus the same thing. Okay, but we combine the g prime theta with g prime theta star. Because g is continuously differentiable, so g prime remains to be continuous, and theta hat is a consistent estimator. So we know that the p-lane of theta star must be theta as well. Why is that? Because theta is between theta hat and theta, right? So theta, so when theta hat, so when n goes to infinity, theta hat will converge in probability to theta, and because theta star is in the middle, so theta star must converge to theta as well. So we know p-lane theta star is theta, and p-lane g prime theta star is g prime theta. Right? By continuous mapping theorem, we know this is true here. Right? This is true. So that means this guy will be 0 when n goes to infinity. So basically we can write like this. So g prime theta star times the square root of n theta hat minus theta equals g prime theta square root of n theta hat minus theta, plus this is small op1, and of course this is just big op1, and the whole thing apparently will converge in distribution to n0 g prime theta square, it's just scalar, and times v. Because this guy will disappear, and the whole thing will just become this is just a constant, right? This is not random, so of course a normal distribution times a constant is just remain to be a normal distribution with the square of the constant times its variance, right? Because let's say x is a normal distribution, then ax is a normal distribution with a squared v. So it's actually very straightforward. So once we know the delta method, we can construct nonlinear vortex. So let G hat be G theta hat. Now, so the G theta hat and G theta is the thing we want to test, right? So we can construct this quadratic form, and it will still converge in distribution to a chi-square distribution, right? Just in the middle, this is our new variance here. Okay, and the G here again, let's say this is actually the, so G is the Jacobian, which is the first derivative of G, right? So this is, so the big letter G actually is the Jacobian matrix, which is the first derivative of the function G. Right. Say we want to test G theta equals 0 versus G theta is not 0, then we can easily calculate a wall statistic like this, right? Because this will just be 0. Of course, in general, it could be any number or any vector. It could be 1, it could be other vector. But you can easily construct a wall statistic like here. And the variance here is calculated based on the Jacobian, which is called the delta method. So in fact, the wall test and the delta method is the default method for hypothesis testing in software like Stata. There are other common tests we will see later in the second part of the 4A, like the likelihood ratio test or the LM test, the Lagrange multiply test, which is also called score test.